Late 1970s, a Terex 3319 Titan hauls 350 tons out of a Canadian pit mine. One machine, one V16 engine, over 3,300 horsepower. Only one was ever built. It never touched a public road, and it never could. A forbidden giant, engineered so perfectly for one job, it became incompatible with every shared system beyond the mine wall. The question is why that keeps happening. When an industrial machine grows to hundreds of tons and thousands of horsepower, it ceases to be a simple vehicle and becomes a mobile geological force. For decades, the economic logic in heavy industry has been straightforward. Larger capacity lowers the transport cost per ton. This financial drive has produced record-setting machines that redefine what steel and diesel can achieve. But this engineering ambition eventually collides with a rigid physical boundary. Public highways, bridges, and tunnels were designed to shared, standardized limits. They are built for ordinary commerce, unable to absorb the massive axle loads and physical dimensions of these specialized giants. This mismatch raises a fundamental question. At what point does technical progress stop serving the shared networks that support society and start overwhelming them? The assumption that bigger and more powerful always represents progress ignores the limits of the concrete and steel beneath the wheels. When a machine becomes too heavy for the public road, it is exiled by physics and regulation. The rejection of these machines by public infrastructure is a matter of basic physics and structural engineering. Civil highways are built around rigid, standardized design limits. A standard paved road is engineered to withstand a maximum axle load of around 9 metric tons. When a truck's axle weight exceeds this limit, pavement damage does not scale linearly, and it escalates exponentially. A single pass of an overloaded industrial vehicle can cause more structural fatigue to asphalt than tens of thousands of passenger cars. Bridges present an even more uncompromising barrier. Most highway spans are rated using live load standards like the HS20 model, designed to support a total distributed weight of around 36 tons across multiple axles. Placing hundreds of tons onto a single span risks immediate structural deflection, concrete cracking, or total deck collapse. Apart from weight, basic geometry and kinetic energy isolate these giants. Standard highway lanes require vehicles to negotiate a 12-meter turning radius, a physical impossibility for rigid frame vehicles measuring over 15 meters in length. Braking systems face similar limits. Stopping several hundred tons of moving mass generates extreme thermal energy. While heavy mining trucks can utilize advanced retarders, a full emergency stop on a highway would overheat their mechanical brakes, requiring minutes of cooling to prevent complete brake fade. Ultimately, these constraints create a hard boundary. What is highly productive within a closed, privately maintained mine or desert becomes structurally destructive when placed on a shared, publicly funded network. While some trucks are born too massive for the asphalt, others are slowly squeezed out by shifting standards. The Scania T-series represents this gradual exclusion. As a heavy-duty conventional cab truck, the T-series featured a prominent front bonnet, placing the engine ahead of the driver. This traditional layout offered excellent ride quality and straightforward maintenance, making it a favorite for regional hauling. The business model for bonneted trucks collided with strict physical space limits on European roads. In July 1996, Council Directive 9653 EC capped the maximum length of standard tractor semi-trailers at 16.5 meters. On a conventional truck, the front hood occupies substantial space within this total footprint, reducing the allowable cargo space of the trailer behind it. Cab-over designs, which position the driver directly over the engine, save all available length for the trailer. While the T-series remained technically legal to drive, its payload disadvantage made it increasingly impractical for operators. This commercial pressure intensified in October 2005 with the introduction of Euro 4 emissions rules. Meeting these targets required large selective catalytic reduction catalyst and diesel particulate filters. Fitting these bulky systems under a conventional bonnet required expensive structural redesigns. Given the declining demand, the development costs made no financial sense. Scania ended T-series production in October 2005, focusing future production entirely on cab-over designs. While some vehicles were slowly squeezed off public asphalt, others were born completely separate from it, shaped by environments where paved roads did not exist. In 1957, French manufacturer Berliet designed the T100 to conquer the sand dunes of the Sahara. Built in secrecy for oil field exploration, this 100-ton, 6x6 giant stood 5 meters wide. It was powered by a 28-liter Cummins 512 engine generating 600 horsepower. It rode on oversized, low-pressure tires designed to float across shifting sands, making standard highway lane and weight limits completely irrelevant. For heavy industrial transport, the Nicholas Tractomas 10x10 pushed mechanical scale to another extreme. Built for heavy haulage of oversized industrial components, this prime mover utilized a 912 horsepower Caterpillar 512 engine to pull loads up to 1,000 tons. Its massive physical width and exceptional axle loads guaranteed it would never share a lane with standard commuter traffic. In the high-speed arena of off-road racing, the KAMAZ 4911 represents the competition branch of this isolation. Built for the grueling Dakar Rally, this 4x4 machine paired a reinforced chassis with a high-output 700 horsepower turbocharged engine. With a near-perfect 50-50 front-to-rear weight distribution, it was engineered to jump dunes and absorb violent impacts at speeds over 140 kilometers per hour, far beyond the safety parameters of any public highway. Each of these machines proves that extreme environments produce highly specialized tools. They did not bypass road regulations, they simply operated in worlds where those rules had no reason to exist. At the apex of modern open-pit mining, the drive for scale has established a permanent ceiling of heavy industrial haulage. The Caterpillar 797F and the Komatsu 980E5 represent this extreme limit. The 4,000 horsepower Caterpillar uses a portal axle design to support a gross vehicle weight of over 600 tons, rolling on massive 4-meter tires. Its direct counterpart, the Komatsu 980E5, pairs a 3,500 horsepower engine with an alternating current electric drive system to move a 363-ton payload. These specifications are not designed for roads. They are engineered for mine-scale productivity where transport costs decrease by 30% per ton. For these machines, road transport is a structural impossibility. They are shipped to site in pieces on flatbeds, assembled inside the mine, and remain confined to private haul roads for their entire operational lives, proving that maximum performance requires complete isolation. These giant vehicles are not engineering failures or design mistakes. They are the entirely logical, highly rational endpoints of industrial economics. Within closed private networks, increasing the physical scale of a haul truck lowers transport costs by 30% per ton. The market continuously rewards this efficiency, driving engineers to design machines that extract maximum physical work from every drop of diesel. But this relentless pursuit of industrial performance eventually collides with a rigid structural boundary. The moment a vehicle's optimized dimensions and immense axle loads require the physical destruction of the public highways, concrete bridges, and tunnels designed for shared ordinary use, it is exiled. Technical progress stops serving the public interest at the exact moment its specialization overruns the common infrastructure that society depends on. To join us in uncovering the hidden systems and overlooked risks of industrial progress, subscribe now. Today, autonomous haulers are pushing these exact same boundaries. As technology scales, the tension between industrial power and public infrastructure only intensifies. Subscribe to join us as we uncover the hidden risks and overlooked systems of our next industrial shift.